Okay, in this lesson we're going to look at two things, the conditional probability and the multiplication rule. So, vocabulary, independent events. So when two events are independent, event A has no effect on event B and vice versa. Like flipping a penny. You flip a penny and get a head, and then you flip it a second time. Your result on the first toss has nothing to do with what's going to happen on the second toss and vice versa. So a penny doesn't have memory. It doesn't say, I'm due a head because I haven't had a head in a while. And when they are independent, to find the probability of A and this little intersection symbol, we can sometimes use the English word "and" for that. The probability of event A and B, we just multiply those probabilities together. So for instance, flip a coin 2 times. What's the probability we get 2 heads? So rather than listing out the sample space, which I'll be honest is probably what I do on this one in the beginning, I may have done that in an earlier lesson, let's use the notion of this independent events. So I'll often use these little blanks here. And we want to get a head on the first toss and a head on the second toss. So we just ask ourselves the question, first, are these independent? Yes. Me getting a head on this one has nothing to do with me getting a head on the second one. So I just find these individual probabilities and multiply them together. So the probability I get a head on the first toss is 1/2, and the head on the second toss is also 1/2. And then I multiply those together. In general, when we have an "and," we're going to do multiplication. We have an "or," we're going to add. So 1/2 times 1/2 is 1/4, which is the same thing you get when you list them out. Now, and it's sometimes easier if you just list them out. But I'm trying to show you an example that's sort of tangible, because later on, if I say I flip a coin 10 times, you don't want to list out all that. That's over 1,000 different outcomes. Again, we have one successful outcome divided by 4. Sort of corroborates our answer there. If they're not independent and it's sort of conditioned on something, we can say the probability of A and B is the probability of A times the probability of B given that A has occurred. This is sometimes hard to get at, but it shouldn't be in this class. It's the probability of A, probability of B given that A has actually occurred. So to find the probability of drawing 2 aces in a row from a standard deck of cards, with replacement and without replacement, just to illustrate the difference here. So picture you've got the deck, you're going to have 2 aces, you want that one to be an ace, and then the next one to be an ace. So the probability I get the first one to be an ace, how many aces are on a deck? There are 4, divided by the total of 52. Now then I put that ace back in the deck and shuffle it back up. So now these events are independent, right? And I can just multiply them right out. And we may want, if we're using we can use a calculator on this one. If we weren't, we would reduce those first to 1/13 times 1/13. But let me show you on the calculator. It does not freak out if you don't want to do that. Times 4 divided by 52. We get a decimal, but we can often, if the decimal's not too, fraction's not too big, we can convert that back to a fraction. We get 1/169. Okay, so that's about 0.0059 was 1/169 as a fraction. Now part B says without replacement. So I get the first ace, and then I hold that ace, and again I get the second one. So again, I'm still doing ace here and ace on the second one. So the probability for the first one is still 4/52. But now I'm not putting that ace back in. So how many successful outcomes? How many aces do I have in the deck? I have 3. Divided by the total number of cards. How many cards do I have in the deck now? Remember, I've got the ace in my hand. I have 51. And then I multiply those together. So 4 divided by 52 times 3 divided by 51. And we'll go ahead and convert this to a fraction. 1/221. And if you wanted a decimal of that, there's probably a key for that, but I'll just go ahead and say 1 divided by 221. 0.0045. and we'd expect it to be a little less likely than this one up here, right? Because I'm not putting the ace back in. I have no chance of getting the ace that I just drew again. Okay, at least one. So often we want to know what's the probability of getting at least one of something. And typically the easiest way to do this is to find the probability of none and then subtract that from 1. And hopefully you'll see that in an example here. So a couple plans to have 12 children. What's the probability there will be at least one girl? So at least one girl. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at least one girl means what? That's a girl, or that's a girl, or however many girls that I have. That at least one of those is a girl somewhere. So really I want to find out the probability of no girls, of all boys. And then subtract that from 1. So it's 1 minus the probability that I get no girls. And this little line above the G means the complement. And in this case, we can convert that back to 1 minus the probability. If it's not a girl, it has to be a boy. They're not always that easy. So 1 minus, what's the probability of getting, and this really should probably say all boys, that every one of those, that I get 12 boys. So what's the probability that the first one's a boy? And I can do my blanks again. We can start it off up here. Is 1/2. How about the next one's a boy? 1/2. How about the next one's a boy? 1/2. We're assuming independence here. All the way out 12 times. So this is really 1/2 to the 12th power. It's 1/2 times 1/2 times 1/2, 12 times. So let's put this on the calculator. So 1 minus, we'll use parentheses here, 1/2 raised to the 12th power. So it's pretty likely we would expect this, right? I mean, they have 12 kids that have at least one girl. We get about 0.99976. So very likely to get at least one girl. Be similar to saying getting at least one head when you toss a coin 12 times, or at least one tail. Okay, so this is called conditional probability. When we have this probability of B given A. I can actually solve for that, and I've got a formula to find the probability of B given that A has occurred. We don't often have to use that in this class. This is not a probability class, but it's there if you need it. So let's look at a sort of a mixture of a bunch of these problems. So a jar contains some marbles, 5 red, 3 blue, 6 black, 4 white, 2 green. Suppose 2 marbles are drawn without replacement. Find the following probabilities. Because in this class, we're often going to be able to count these outcomes. Okay, so let's find the probability of a blue on the first draw and a red on the second draw. So I'm going to have to write these down. So we had 5 red, 3 blue, 6 black, 4 white, and green. So one thing I need to find here is obviously the what? Right, I got to find the total. So 5 3s, 8, 10, 20. So I've got a total of 20 marbles here. So a blue on the first draw, and, so whenever you see that word and, you want to think it's most likely going to be a multiply, and a red on the second draw. So a blue on the first draw. So we want that one to be a blue, and we want the second one to be a red. And this is without replacement, as you'll recall. So what's the probability I get a blue on the first draw? How many blues do I have? I have 3 divided by the total of 20. And then how about the red on the second draw? So given that this is a blue, what's the probability I get a red on the second draw? I've got 5 reds divided by a total of 19. And then I multiply those. So let's bring this calculator up. So 3 divided by 20 times 5/19. And we'll just keep this as decimals, 0.039, we'll say. Okay, how about a white on the first draw and a white on the second draw? So white on the first draw and a white on the second draw. So how many whites do we have? 4 over 52 times a white on the second draw. How many whites do I have in the deck now? I mean, how many white marbles do I have in the, not 52, hold on a second. I know some of you were screaming when I put that 52. I got my head in the cards. So 4 over 20. Now I've got the second one white. How many whites do I have left? I've got 3 divided by 19. And I multiply those together. 19 because I'm assuming that I have this one white. That's how I determine these probabilities. So 4/20 divided by, times 3/19. 0.032. Okay, at least one white marble. So at least one white marble. It's easier if you'll do 1 minus no white. Because if you do at least one white the other way, you've got to find out that if this one's white, this one's not white, this one's not white, this one's white, or that they're both white. So that's 3 separate events we have to actually calculate. So it's easier to find the probability of no whites and then subtract that from 1. So what's the probability that this one here, this first one, is not a white? And the second one is not a white. I'm going to do it up here. It's not, my pen's not wanting to work down there. So this first one is not a white, and the second one is not a white. So how many are not white in our bucket here of marbles? Well, 4 are white, so that means that 16 over 20 on the first one. I'm not replacing it. So how many do I have that are not white, assuming that I get one of these? I now have 15 over 19. And I'm going to do 1 minus that. So 1 minus 16 divided by 20 times 15/19. And we get 0.368. Again, this is the answer for C. Okay, guidance counselor in middle school collected the following information regarding the employment. And we've seen this in an earlier lesson if you watched that. So we've got a few more ways we can ask questions now that we know about conditional probability. So the probability that both spouses work given that they have 0 children. And the probability they have 0 children given that they both work, and the probability that only the wife works given that they have 2 or more children. Okay, so what is the probability that both spouses work given that they have 0 children? So what we do on these is I always look at the given first. So given that they have 0 children, so we know that we focus in on this column only. We don't worry about anything else over here. So given they have 0 children, what's the probability that both spouses work? So only look in this column that I've just circled. How many successful outcomes? How many do actually hit in that class? 522. over its total, because we know that they're only 788. If you do it this way, it's a little bit easier, I think, and you don't have to use that formula. You can go back and use the formula. I don't want to show it to you, but it can become kind of a mess if you do. So if you can do it this way, it's much easier. I may make a separate video on how to use the formula if I find students need it. And then we convert that to a decimal. So 522 divided by 788. So about 0.662. Okay, what's the probability that they have 0 children given that both spouses work? So what are we going to do now? We know that both spouses work. So we know we are focused in on this row right here this time. So only focus on the row, don't focus on anything else over here. So what's the probability they have 0 children? 0 children, 522. Divided by 1149. So we see that the probability of A given B is not the same as the probability of B given A in most cases. So we have 522 divided by 1149. 0.454. What is the probability that only the wife works given that they have 2 or more children? See if you can do this one on your own. No help from me. All right, welcome back. I know you paused it. So, given that they only have 2 or more children, where are we going to focus? 2 or more children, right? So I'm going to focus right here. 2 or more children. Now what's the probability? So we're not going to look at anything else. What's the probability that only the wife works? 15. See? That's not hard, is it? 15 divided by 559. 0.027.